name is Josiah Hanna. I have the privilege to introduce Professor Peter Stone. So Peter is the Touchard Foundation Chair in Computer Science at the University of Texas at Austin, and he's also the Chief Scientist at Sony AI. Peter has an extensive list of service to the AI community. He's been the chair of numerous conferences. He was recently the president of the RoboCup Federation, and he's the chair of the Standing Committee on the 100-Year Study on AI. His research has won numerous awards, for example, the prestigious IDGCAI Computer and Thought Award, the ACM SIG AI Autonomous Agents Award, and he's a fellow of AAAI, IEEE, the ACM, and AAAS. One aspect of Peter's work that I find particularly inspirational is how he envisions the ways in which we will interact with AI in the future, and then takes on the challenges to realize that vision head-on. So this approach has led to pioneering work in, for instance, transportation systems for autonomous vehicles, RLHF, before it was really cool to work on it, and a number of really really robotic systems. Peter's not only a great scientist, but he's extremely supportive of those around him, and I know there's many people in this room who've benefited from knowing Peter. So with that, please help me in welcoming Peter.
Thanks. Thanks, Josiah, for that kind introduction. Thanks to the organizers for inviting me to give this talk, and also for all the work that you've done to really build this community that's definitely not a cult. This is it's really it's an exciting venue to be giving this talk. There's some of my mentors are sitting in the room who've inspired the work that I'm going to talk about. As Josiah mentioned, many of my mentees, without whom this work wouldn't have been possible at all. My most cherished colleagues, and many people who I count as my closest friends. And so it's really a pleasure to be here. Like David this morning, and many of you in this room, I do have the goal. I share the goal of trying to help create superhuman AI. And I reflect on sort of, if and when that happens, or it is happening. It's happening in many domains, and every time it does, there's sort of going to be the first time it happens, and then probably a little ways down the road, there'll be the more pure way it happens that sort of is more true to heeding the bitter lesson, and maybe does even better. And this talk will sort of focus on that, trying to that first time, the lessons that are needed when you're sort of pulling together all that you can to get, just eke out that superhuman performance for the first time. And I think that's a necessary step that will be also along the way to the more pure way of doing it. So this talk is in two parts, and in the first part, I'm going to ignore the very sage advice that's been given to me many times, which is in a talk like this, you should pick one or two things and go really deeply so that people understand all the details. Don't try to say too many things. I'm going to go to the complete other extreme, and I'm going to tell you almost nothing about a whole lot of things. Some of the talks, some of the slides, there's whole dissertations on, or I've given 1-hour talks on them. But I'm going to try to organize it in a way that makes that sort of puts together these the lessons in a way that gives you some structure. And then in the second part of the talk, I will do more of a deep dive on one of the more exciting things I've been a part of in the last few years, which is GT Sophy, and that's going to be also demonstrated in the industry mixer later. So, because of this, I guess it's sort of convenient that it's going to be a bit of a whirlwind. If you lose attention, you'll sort of miss something. But then the next slide there'll be something completely new, so you'll be able to snap back to attention, and all the references will be here. And it's mainly to give you sort of pointers to follow up in more detail on things that you may have forgotten about or may not have known about. And I hope it achieves that. So, okay, so let's dive in. So first of all, I just want to tell you a few things about the exciting things going on at UT Austin. We got one of the first NSF AI institutes on the foundations of machine learning, led by Adam Clivens, and used that to found a machine learning laboratory. There's also a very exciting AI for Good initiative called Good Systems that I've been a part of, that's inspired by the 100-year study on AI that I was until recently the chair of the standing committee of, and that I think has had a lot of good things to say over the last few years. And I also serve as the director of Texas Robotics, where we had a ribbon cutting on a beautiful new building in just a few years ago. I hope many of you will be able to come and see it. So the driving question that's sort of pushed me along in my research is the one that's summarized here, a little more specific than superhuman AI as a whole, but it's really, I think, an important part of it, important direction. It's my sort of North Star. And this has really appeared on almost every talk I've given since my PhD thesis that's more than 25 years ago. And it's to what degree can autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains? And so to answer this question, my research group has published in many different sub-areas of artificial intelligence. And of course, with this kind of a question, reinforcement learning is really at the core. And we've published a lot of work on that's sort of more theoretical and algorithmic, that I call sort of bottom-up research. But also I've done a lot of work that's more top-down or use-inspired in many different domains. Some of the ones shown here. And I was just at RoboCup just 2 weeks ago, where Josiah and I had a joint team that came home with a trophy, playing in settings like this one, where the robots are autonomous and having to sense, decide, and act, where they have teammates, where they have adversaries. This was the finals of a competition several years ago, where we ended up beating a team from the University of Bremen. And of course, you have to remember these robots are fully autonomous, no remote control. And here our robot goes in on a breakaway, and you'll see it calmly bank the ball off the goalpost and in. And of course, the goal of RoboCup, one of the sort of inspirational goal, is by the year 2050 to create humanoid robots that can beat the best World Cup champion on a real soccer field. And so that's a superhuman AI goal. It's to try to create soccer players that are better than people. I've also thought a lot about. I've been inspired by general purpose service robots, ones that this kind that wander around the hallway on their own for hours. And I've also thought a lot about, been inspired a lot by the challenges of autonomous driving. Thinking about what the intersections will look like when we have all autonomous cars. Will we need traffic signals and stop signs anymore, or can we have intersections that look more like this? I could talk forever about any of those applications. You'll see some of the work, though, that's been inspired by that. And then I also mentioned GT Sophy, which I'll come back to at the end of the talk. So in this talk, as I sort of alluded to already, I'm going to be thinking of RL as a tool. As like, how can we use it to achieve specific tasks or specific objectives? And so rather than, this is sort of as opposed to thinking of it as a sort of agent architecture. It's both, but I'm thinking of this as sort of a tool in the toolbox of AI researchers. We're trying to achieve things in specific domains. So rather than starting from the sort of simple and most abstract models and think about what is guaranteed to work, and then just and then trying to apply it and hoping that it works in the more complex settings, I'm going to sort of embrace the idea that we're in the full complicated world with state aliasing and generalization from the beginning, and think about what are the tools and methods that we need to use to learn in that setting, and then try to apply there. So rather than asking, should reinforcement learning work, I'll be thinking about, does reinforcement learning work, and when not, how can we make it work? So as I said, I'm going to be giving this sort of whirlwind that focuses on a lot of the work that I've been involved in, but none of this is unique to my lab, I think. And in fact, in many of the talks that we've already seen yesterday and today, many of the same themes have come up. But I'm going to organize this idea of practical reinforcement learning along these 4 dimensions. That if you take the P here, also makes a nice acronym of PRISM. But that's representation, and that's choosing the algorithm to suit the problem, and also learning or evolving the representation to suit the problem. So Sergey talked about pre-training to learn the representation, and David talked about meta learning to try to learn the algorithms. Those themes come through in this category. And then I'm also going to talk about interaction, where when an agent has to interact with other agents, that can make life a lot more complicated. But it can also be, interaction with people can be simplifying, and that's been a theme over many years. And of course, both Finale and Emma talked about reinforcement learning in the context of people either being the problem, or providing the data, or being some of the input to the problem. And then there's synthesis, decomposing problems to use multiple algorithms, and also synthesizing concepts. David also gave some examples of that, especially in the alpha proof, where there's the translator, and then there's the prover, and there's some planning involved, and there's some of the learning involved, of course, as a central aspect. And then maybe a somewhat odd way of putting it, but I think it's an important concept, is also the concept of mortality. And I think of that as meaning what Doina said at the beginning, that our agent is small in a very big world. Or as David also said, the world is vast. And that's the same for us, that we're not in our lifetimes able to explore everything in the world. There's far too many things, far too many places, and that's true for our agents as well. And so it's important to leverage the past, and also to acknowledge a finite future. You can't even try everything once before you decide what to do. And then an important lesson for practical RL, of course, is to build agents, to get experience with actually making things work, and trying to see what does and doesn't work. Okay, so here starts the whirlwind. So representation, choosing the algorithm to suit the problem. The PhD thesis of Shivaram Kalyanakrishnan back maybe 14 years ago now did, I think, provided a very nice template for this kind of, for studies that can get at this kind of a question, where he was, at that time looking at lots of different learning methods that are shown here, and then thinking about the many different problems that these algorithms could apply to, and then thinking about, if you're given, if you draw a problem from the distribution of possible problems, what would be the algorithm to suit it? And we still, I think we still as a community need to make more progress towards this, mapping the various different algorithms we have to the problems. Of course, it would be nice if there's one general purpose algorithm that does everything, but we're still not there, and so we still need to be able to do this in a more systematic way. And what Shivaram did was created some small parameterized learning problems where he could very systematically vary the size of the state space, the stochasticity and the transitions, expressiveness of the function approximator, generalization width, and state noise. He then took 2 representative algorithms from the value function-based and policy search-based algorithms, and then varied across all of these dimensions. These are just 3 of the graphs. There's many, many different graphs in this MLJ article from 2011 that vary as sliders each of these dimensions, and looks at how that affects which algorithm is going to do better on that problem. I think this is, this is a template for how we can, take. It needs to be repeated. I think, algorithms have changed, problems have changed, but I think this is a very worthwhile piece of work to look at and to emulate. Also was some work of Nate Cole and Peggy Fiddleman. We were looking at ways to use reinforcement learning to have robots learn without a simulator, with all the learning done in the real world. And for that, we needed to have an algorithm and also a state space that was very low dimensional, because there wasn't going to be a lot of experience. And so This work made a splash back in the, I think 2004 or so, 20 years ago. We had robots learning to walk. The fastest anybody got these old Sony Aibo robots to walk, using a version of policy gradient reinforcement learning, where we didn't have to do any intervention. We just put the robots on the field, had them practice walking back and forth, and by the end they got to the fastest known walk on the robots. We also used a similar methodology for learning to control the ball, and it's the robot, both trying to see if it could control the ball under its chin, and then pushing it away to create another learning example for itself. And the key here was first of all a low-dimensional state space where we were learning the not just the joint angles itself, but actually the locus, the shape with which that the legs should be moving through when walking, parameterized as an ellipse, and then there were parameters of that ellipse that was being learned using an efficient gradient approximation. And so this was, there was no way that a value function-based method was going to approach this problem. And then similarly, Matthew Hausknecht started looking at using hybrid action spaces to deal with partial observability, both in the robot soccer domain and in a partially observable version of Atari, where the screen was flickering. Where we looked at learning the action class and its parameters together, and then using recurrence to cope with partial observability. And of course, all of these ideas have been picked up, and like I said, we're not the only ones to have explored them, but I think it fits into this theme of trying to think about what's the problem, and then what's the algorithm that's gonna suit it. With regards to learning the representation, Shimon Weizen's thesis introduced an algorithm called neat plus Q, where the idea, I think it's very much like the meta learning that David was talking about, where it's I think one of the first examples of what today is called neural architecture search, where the idea was evolving agents that are better able to learn, where there was an outer loop of neuroevolution of augmenting topologies, or the NEAT algorithm from Risto Mikulanen's group, learning the structure of neural networks, and then evaluating not how well they did at the problem, but how well they supported learning as a function approximator for Q-learning. So every learning trial would draw a new neural architecture, put it into a learning agent, have it go through a whole lifetime of learning using that architecture, and then that would evaluate, that would create the fitness for that neural architecture that would go back into the pool for new generations. And this was at a time when the conventional wisdom that was that if you used neural networks as a function approximator for problems like mountain car, that you would always diverge, that you'd learn for a little while and then you'd just start getting worse and worse. The only way we could get Q-learning to work was just to really aggressively anneal the learning rate, so that so that it just sort of flatlined. Otherwise, it would start tanking. But it turned out it wasn't a problem with Q-learning. It was a problem with the topology of the function approximator, and this neat plus Q found a very non-standard topology that ended up supporting, sort of as for each new generation, you'd sort of learn for a while and then start tapering, but then you'd start a new batch of Q learning agents with a new function approximator, and end up doing much better. And so we did better than any of the manual configurations we could come up with, and I think it was the first example of neural networks function approximation working on a continuous state space task like mountain car. And then much more recently, I've been doing work and I've been showing, by the way, the pictures of the students who are involved in this work. I've also had colleagues that I'm collaborating with. This work, especially on this slide, is collaborating with Amy Zhang and UK Zhu and Roberto Martin, but we've been looking a lot at causal dynamics learning, trying to use reasoning about causality, what kinds of state variables impact others, to learn task-independent state abstractions and then leverage them for downstream tasks. A method called causal policy gradient that's using in-factored action spaces being used for whole body mobile manipulation, that's sort of separating on a mobile robot, reasoning about what actions control your motions, what control your sensor perceptions, that would be the camera on the swivel, and what what actions, parts of your action space control manipulation, and separating those so that you're not trying to learn in such a high-dimensional action space, but not doing it manually, allowing the robot to learn through experience how to separate the different action dimensions and then use that again for the downstream reinforcement learning. And then similarly using exploring to discover local dependencies, when these kinds of causal dependencies, where in the world they apply, and then planning actually to try to discover what variables impact what. So some of the, again, these are just hints at the depth of the work, but these are all much more recent papers that you can find in the references down here. So in this theme of representation, I do think this is just a really important thing to embrace when we're trying to do practical reinforcement learning, choosing the algorithms to suit the problem, acknowledging that there's going to be different properties of the different problems, and then also this notion of the representation being learnable and then usable for downstream tasks. So switching themes to interaction, I said there's sort of two components to this. Multi-agent interaction can be very complicated, but input from people can be simplifying. So Rich a while ago posted his picture showing that he's laser focused on the concept of intelligence, and I can't remember the words exactly that went along with it, but he's always remained laser focused. And but I had the pleasure of collaborating with him on some work in the robot soccer keep away domain, which was a multi-agent setting that looked like this. This was sort of the random behavior before learning, where these red players were learning to try to keep the ball away from these blue players. They're both going to the ball because one of them can't get the ball away from a red player on its own, so they're sort of doing that together. But the actions here were each agent learning independently, and we found that they were able to learn together. But we tried two different settings. One where the behaviors of two of the yellow agents were fixed, and the others, and only one of them was learning. And we would get learning curves like this blue curve. But as soon as two were learning or three were learning at a time, even two though, it became much more difficult. So this notion of and here's what it looks like after learning. The red players, not the yellow players, but the red players, after they've learned for about a day or so in compute time of 2002 or so, they were able to get much better performance, better than the hand-coded policies we could create in this domain. But it was an important lesson that when you have the multiple agents learning at the same time, it became a much more complicated problem. So I've done a lot of work at sort of analyzing this kind of a setting. And Doran Chakraborty had a really nice, more theoretical analysis of optimal multi-agent learning that was sort of embracing the idea that actions can serve, when you're in a multi-agent environment, can serve two purposes. There's the usual reinforcement learning purpose of trying to yield immediate or delayed payoff, trying to get some to move to a particular place in the domain and getting rewards. But there's also the purpose of training the other agents, making them know what to expect, right? And that you can that an optimal policy will, if you're in a competitive setting, would lure the other agents to learn some exploitable behavior that you could exploit later. Or you can, in a cooperative setting, if you might. If you come across a new driver who's never seen the concept of a turn signal, you might train them by every time you're going to turn in your car, turning on your turn signal, and they'll learn pretty quickly to be able to use that as a way of predicting what you're going to do in the future. So in that case, you're trying to be helpful and let the other agents predict what you're going to do so they can behave better. And so Doran came up with a beautiful algorithm called Seamless Convergence with Model Learning and Safety. That was the first multi-agent learning algorithm that would converge to a Nash equilibrium if all the agents were using it, but that would achieve targeted optimality, which is a concept that means that they would converge to the best response against any agent in a particular class of policies that they might be using, which was memory-bounded adaptive agents. So the ones that are, if you know game theory, playing basically a form of fictitious play. but also the property of safety, that if you were playing against anyone, that you could, in a pack sense, probably approximately correct sense, you would never do worse than minimax. And so these are, it sort of protects against the worst case. And so this is very theoretical. We did try to apply it in some cases as well, but it's I think something that's been sort of underappreciated over the years, and I think could be picked up. There's some nice hanging threads there for people who want to look for new research topics. And then this has also led to something that I've been really focusing deeply on over the past 15 years or so, that is really about interaction as well. At its core, it's ad hoc teamwork. The idea of trying to get agents to be able to cooperate with teammates that they've never seen before, but on a domain that everybody sort of has experience with. So the idea of, I can go play a game of pickup soccer with people I've never seen before. I don't even necessarily speak the language, but we can just jump on the field and start playing, or some of you may play pickup basketball or something like that. And this is something that we can do as people, and it's also in like a disaster rescue scenario, right? If there's an accident on the street, a bunch of strangers can come together and immediately figure out who's going to check if the person's okay, who's going to call 911. We're very good at forming teams on the fly, but our agents over the years have not been. And so this is, I think, a really nice challenge. And it's important to when you're thinking about this problem, to embrace the idea that your teammates are likely to be suboptimal. You don't have control over them. You can't say, I want you to be better. You just have to say, what can I do in the context of these other agents? And so there's a modeling aspect of this, figuring out quickly what are they good at, what can they do, what are they going to do, and then sort of a modeling, that's the agent modeling, and then sort of a quick planning component. And you need to have learned prior a bunch of, a way to deal with very different classes of agents. So the idea, the challenge is creating a good player, a good team player, with all of the learning you want in the background that can then immediately be deployed and work with whatever they're faced with. We've looked at this as I introduced this problem as a challenge problem in the challenge problem track of AAAI in 2010. We've analyzed this theoretically and then also looked at it in some sort of empirical settings, both in the predator-prey domain, where we took a bunch of human-created teams of 4 agents and then replaced one of them, shown with the yellow star here, with an ad hoc teamwork agent that had to figure out how to work with whatever team they were given, and also sort of soccer teams where we replaced one agent on the yellow team with the green agent, and again, it had to figure out how to work with whichever team it was given. Katie Genter did her thesis in a problem that was inspired by this problem, the idea of if you have a bunch of birds that are sort of flocking, and you can insert some of them, the ones shown in pink here, and you could control them, but they're seen as members of the flock. Could you somehow control the flock? It's inspired by what if you can get birds, can you get birds to fly around an airport where they were creating hazards to airplanes? And where would you place the sort of the controlled agents, and how would you control them as a function of the way the teammates respond to them? And we've also looked at this in the robot soccer setting as well. So there's some drop-in. There was a drop-in challenge where teams from different players from different teams were put on the field together, and they had to without any coordination ahead of time, figure out how they were going to work as a team. And so the players were programmed to like look at their teammates and see what role should they play given who they're playing with right now. And then this has inspired many different variants of the problem. Some people have looked at ad hoc teamwork with communication, when you can communicate with your teammates, either emergent communication or costly communication, and also very recently we're looking at the problem of what if you don't just have a single agent that you're controlled, but there's a sub-team. We call this the N-agent ad hoc teamwork problem, where there might be 3 or 4 agents that can coordinate very tightly, but then they're have to work with a bunch of other teammates that they've never seen before, and this sort of a generalization of the ad hoc teamwork problem that's been worked on before. So that's sort of where interaction becomes complicated. But there's also, I said, interaction with people can be simplifying, and this was first sort of brought to my awareness through Brad Knox's work, one of the organizers here today. He introduced the tamer system. The first domain we use this in was in the game of Tetris, which was a domain that at the time a reinforcement learning algorithm could do very well after hundreds of thousands of games. But in this video that starts from random behavior, and in the top left corner, it's flashing red when a person is saying that it was a bad move, and green when a person says it was a good move. And after just even in the middle of this first game, it's starting to do much better than random. And then when we get to the point of, I think 3 games in, it's able to just start clearing many lines at a time. So it's getting sort of making reinforcement learning much more sample efficient by leveraging the human reward signal. And so the lesson we saw there was that this allowed much quicker learning than having to learn from scratch, but sort of consistent with the bitter lesson and with what David was talking about. If we build in this reward signal, it can hamper what the eventual asymptotic performance would be. So then we looked at ways to put these together, to sort of use it as a prior learning from the human signal, and then allowing the reinforcement learning to take over and do much better. And we've also, with Garrett Warnell, extended it to learning from a pixel-based representation. And I really think this is the first example of what has come to be known as reinforcement learning from human feedback. And Brad really gets credit for doing this. I admit I was very skeptical that this was going to be a fruitful research direction at the start, and Brad was persistent and convinced me to go down this path. And we've continued. We've also looked at a problem recently of learning not just from explicit human feedback, but allowing agents to try to learn from implicit human feedback. In a situation, if you're in an autonomous car and your passengers look like this, you probably don't need them to tell you that you've done something wrong. The agent should learn from that. And so we have a paper from a couple of years ago called Empathic, which is a clever acronym for something or other, but I can't remember. But it's all about sort of learning from implicit human feedback in this sense, and as an offshoot of this of Tamer. Faraz Tarabi, also with Garrett Warnell and I, extended this to imitation learning from observation, a setting where you're trying to learn to perform a task from state-only demonstrations, again as a way of seeding, a prior to then do autonomous to do RL from afterwards. But in this case, where you only get to see the sequence of states that the agent goes through, you don't get to see the actions that they took. And we have both a model-based approach called BCO, or behavioral cloning from observation, and a model-free version called GIFO, or generative adversarial imitation learning from observation. Again, skipping over many details, but just sort of giving you a hint of what I mean by the sort of the interaction with people can be simplifying. That there's a lot of information that's rich there that we can build on. With regards to synthesis, Shivaram, who I mentioned earlier, extended some of our work that we started in this keep away domain, not just to decide where to pass the ball, but also to decide where the players should go when they don't have the ball. And to do that, it turned out that we couldn't use the same algorithms for both of those components. We used a value function-based method, as we had done with Rich, for the pass problem, but for the get open problem, it was a much bigger, higher dimensional decision space, and so we put together a policy search method for that. And then in a much more sort of sophisticated version of this, Patrick McAlpine built on my PhD thesis from the late 1990s, which introduced a layered learning paradigm where you decompose a problem into multiple different subtasks and use the learning of one problem as input to of one subtask as input to the, or a way to leverage the learning of the next subtask. In my PhD thesis, I did this with three different behaviors in the robot soccer domain. Patrick took this to a much higher level, initially with 19 learned behaviors, but then up to tens and hundreds of behaviors, which I am not going to go into all the details, but one example of this was having an agent learn. We wanted it to learn how to kick the ball. We decomposed it to learn how to first just approach the ball efficiently, like as shown there, and then had it learn if it was in the right position, to, if it had already approached the ball, learn how to kick the ball. So what joint angles should it go through to do that? And gave it lots of examples of that. And then put those together to be able to walk up to the ball. In this case, it's going to dribble the ball for a little while and then kick it. And trying to learn this all end to end was we weren't getting very far with. But when we used this sort of layered learning task decomposition approach, got to a program that was that ended up winning this version of this league of the Robocop competition for 10 out of 11 years, including several years in a row where Patrick had already graduated, was not working on the code anymore. Several teams, all the teams were trying to pass him and couldn't until finally a couple of years ago they surpassed the work that he had done. But if this is the secret sauce here was really using learning for many different sub-behaviors and putting them together. I mentioned earlier some of the work of Doran Chakraborty on that was sort of theoretically oriented and I think left a lot of directions for follow-up. Another line that's similar is Nick Zhang, who he put together this again in the sort of realm of 20 years ago or so, was thinking about how to put together function approximation in continuous states, sample efficiency using model-based methods, and hierarchy. The sort of one of the methods of the time that was leading at the time was MaxQ, and found very elegant ways to combine these, to create fitted Rmax, to put 1 and 2 together, RmaxQ that combined sample efficiency and hierarchy, and then all three in his eventual PhD thesis, an algorithm called fitted RmaxQ. That was learning primitive action models, predicting action effects in continuous space in a model-based kind of way, planning to explore uncertain regions, and then approximating values of abstract actions. Many of these components are coming back in today's most sophisticated architectures. And I told Nick that it was great that he was doing all this theoretical work, but to do a thesis in my lab, you have to have both some theory and then you also have to show make it work as well. And you can't. I told him you can't just make it work in Mountain Car or Puddle World or the taxi domain. You have to make it work in a more complicated domain. And so he came back to me and said, "Okay, I've got everything working in Mountain Puddle Taxi," which put all of those together. And so I let it go. But there's a lot of this was really elegant work, and again I think ahead of its time in many ways. Okay, and then the last sort of lesson, which I said is a little bit oddly named, but I think is I think it's apt, which is that the agent is small in a very big world, which is sort of this we live with this by it's sort of our concept of mortality, that we can't do everything, and this motivates leveraging the past. So there's been a lot of work in my lab. Started when Matt Taylor was a student on transfer learning. And some of the first work on transfer learning and reinforcement learning, where we were taking a function approximator from one task and using that to speed up learning in another task. And then more recently, taking that to the next level of automated curriculum learning. Samik Narvikar did a thesis where it's motivated by where we try to teach kids to play chess by working them through a series of other games, maybe tic-tac-toe, then checkers, or simplified versions of chess. But usually where it's a person designing that curriculum, an automated curriculum learning is sort of taking the idea that there's task creation and sequencing and transfer learning and putting those components together to automatically create curricula, very connected to some of the things Emma was talking about and that we've applied since to the physical domain of physical therapy and trying to help physical therapists figure out what would be the next tasks that a person should do when they're trying to recover from a stroke or learn a new motor skill. And the goal here is to sort of learn a general teacher agent that can create those to help the agent. You could think of it as part of the same agent or an external teacher agent that sort of helping the agent decide what it should learn next. Also, a way of leveraging the past is I guess acknowledging your finite future as being very efficient with the experience in the real world by leveraging simulators and then doing sim to real. Josiah Hanna, who's did the introduction, his PhD thesis was inspired by a method that we called grounded simulation learning that would that sort of embrace that we're never going to have perfect simulators, but rather would try to improve a simulator in the version of policy space where you're currently searching, figure out one gradient step in your policy, and then reground the simulator that would make it faithful in the new part of the policy space where you're searching in sort of a closed iterative loop, and use this to start from an initial policy this was one of the fastest walks on the Now robot at the time. That was going at 19.3 centimeters per second, and then using this methodology where the learning was done in the 3D simulator that I showed you earlier, grounded the simulator, did the learning in that simulation, came up with a walk that was 35% faster than anybody had made these robots walk before, then regrounded the simulator and did another iteration and came up with this walk that's sort of much squatter to the ground, and ended up walking at the fastest that anybody was able to get these robots to move at the time. And this concept was then extended. Ishan Durikar and other colleagues that we worked with worked on trying to ground the simulator again, but now doing it using state distribution matching. In a method that we called adversarial intrinsic motivation, and so I'll leave the details you can find in the papers. And then the last aspect of mortality, this acknowledging the finite future. I think this was really the biggest inspiration for Todd Hester's thesis, where we noticed. That as people, we can't explore everywhere, and that's true for, but in many reinforcement learning domains, we were starting from the idea that an agent should go everywhere, try all state and action pairs. I know that sitting in my office at the university, there's like some buildings I can see out the window that I've never walked into, right? Or I've never gone to the second floor of them, let alone places in other cities, or there's lots of restaurants I haven't tried. We just can't. And so Todd's take, he introduced an algorithm, Texplore, that sort of flipped. Rather than thinking of exploration as deciding what to do next, it was choosing actively where never to go, where never to explore. And he looked at using multiple possible models, comparing them, and only exploring states that we were uncertain what's going to happen. It was a model-based method. So there was uncertainty, but also that according to our model, it was promising that we would learn something of value, and not just something new, but something that would of positive valence, right? We're not going to just drive the car off the cliff to see what happens. We have a model that's probably not going to lead to positive rewards. But doing and sort of being very sort of deliberative and active about which parts of the world to explore, we ended up. Applying this on an autonomous car, trying with a task of just trying to do what a PID controller might do, trying to achieve a particular speed and stay there. It was able to, after just 18 episodes in the real world, about 3 minutes of driving with acting at 20 hertz, was able to do as well as a finely tuned PID controller. And then finally, there's some threads. It's also with this finite future and leveraging the past, we sometimes think of continual learning as meaning you live forever, but I think of it more as you need to be leveraging the past. Whenever you're given a new, you're in a new sort of setting, or there's this ongoing stream of experiences, you can't treat it as starting from scratch. You have to keep leveraging everything that's come before. And so we've looked at lifelong learning for mobile robot navigation. Bo Liu looked at a really interesting problem of continual learning and private unlearning that's sort of in a privacy-preserving setting. And we've introduced a benchmark recently called Libero for benchmarking knowledge transfer for lifelong robot learning. And this notion of continual learning was the basis for a startup company that I founded with Mark Ring and Satinder Singh called Cogitai that eventually led into Sony AI, which I'll be talking about soon. Okay, so that's the main whirlwind, I've broken down sort of these lessons that I've learned over many different sort of research nuggets and applications into representation, interaction, synthesis, and mortality. But also a really important part of practical reinforcement learning is actually putting it into practice, building agents. And over the years, I'm not going to be able to tell you about them, but you've already seen a bunch about RoboCup, robot locomotion. I've mentioned Tetris and autonomous driving. Robotics has been a really big theme for the research. So we've looked at developmental robotics, general purpose service robots. There's also a division of RoboCup called RoboCup at Home where we study this. Mobile manipulation and tabletop manipulation most recently. We actually just last week published a survey on deep reinforcement learning's applications in robotics, and categorized both the work that I've talked about here from my lab, but of the much broader community as well, and also showed where there's still room for new innovations in that space. So I encourage you to look for that. We've also done robotics domains, a lot of work on trading agents and general game playing, Elad Liebman on music recommendation, and a lot of research inspired by traffic flow. But the one that I'm going to spend a little more time going in a little more deeply, it's a little bit of a deep dive in the time that I have left, is GT Sophy. And so I think many of you are familiar with it, but this was a really exciting project that was done by many people. These are the co-authors of the paper that appeared in Nature. I think maybe my biggest role, I've played a role in this, of course, but part of it was just assembling this fantastic team of people who really made it happen. And so we set out to create a result that would be that would take a place in the sort of series of superhuman AI results along the lines of Deep Blue in chess and AlphaGo and Go and Watson in Jeopardy, and tried to focus, I think, for the first time on a task that people really spend their time to become super expert level at. That's a real-time control task, and that's race car driving. It did land on the cover of Nature. And in all the videos and sort of slides I'm going to show you, there's going to be the white cars that are driven by people and the colored cars of various colors that are driven by our agent, GT Sophy. Just like many of the other sort of superhuman results, it relied on having a great compute architecture, lots of data, some really top-notch engineering, and then a few algorithmic and methodological insights that may be generally applicable beyond the domain. But it's it wasn't there is a pure aspect, a purity aspect to this approach that I'll talk about, but it also is bringing together many of the tools in our toolbox to try to do it in the first possible way to just finally get above human level performance. For those of you who aren't aware, this was done in a racing simulator called Gran Turismo. There's a movie out about Gran Turismo that the people somebody who trained in it was able to become a professional Formula One race car driver. To get a good sense of how accurate this simulator is or how realistic it is, this is a top and bottom video of Ken Chan, a professional driver, driving in the real world on bottom and in the Gran Turismo simulator on top, the same car on the same track, and he finishes the lap of the track within 0.1 seconds in the simulator of the time that he did in the real world. And in Gran Turismo, it also models airflow, so you have less air resistance when you're behind another car, tire friction and traction. It's a very fantastic domain. Again, you get to play with it later if you'd like to. The setting we set up for ourselves was to race against 4 of the best Gran Turismo drivers in the world, shown here, on 3 different race car track combinations. And just like the people who practice with the cars and tracks. We allowed the agent to specialize, so it learned how to do each one of these separately. And the approach that we took, well, first of all, the challenges that you have to solve here are, first of all, just race car control on an empty track in real time, having the agent select actions at just at the sort of razor thin edge of not spinning out, going as fast as you can, but having just enough tire friction to make the turns. But then there's also a multi-agent aspect. There's tactics, where you have to decide when to pass other agents and how to block them. There's a whole bunch of skills. And then there's this sort of loosely defined concept of etiquette, where human judges decide whether you were unsportsmanlike by pushing another car off the track or running into them or something like that. So when we set out to do this, conventional wisdom was that this was a task for model predictive control, that you would define a line that the car should follow and then use MPC to have the car try to follow that. And to be honest, I thought that a sort of model-based kind of approach would be useful in this setting, but it turned out that really a pure end-to-end deep reinforcement learning method was the best winning approach here. Literally starting from random behavior, where the car is just running off the track, running into walls, driving backwards, and giving it a very simple reward signal, and using the standard RL paradigm. And within a day, it would get to superhuman performance on an empty track, and within a week, be able to drive competitively at a superhuman level. In the original version, so you saw, some of you may have seen the paper earlier today where we used a state space that would involve pixels, but I think the action space remains the same. It's just a two-dimensional action space, brake or throttle, turning left or right. The rewards in the initial version on the empty track is just incremental progress along the tracks, with penalties for tire slip, moving off the course, and hitting a wall. But mainly just this sort of dense reward of incremental progress. In the first version, we did use features like velocity and acceleration and roll, pitch, and yaw, loads on the tires, and some sort of features of what the shape of the upcoming track was. So here you see like some dots on the purple here indicating at the same time as this car is driving, it would get sort of the left, center, and right for 60 points in front of the car. That's sort of a sliding window. So that would allow it to generalize across tracks as well, in a version where we didn't have it memorized to a track. We used a lot of, like I say, a lot of sort of heavy-duty engineering with cooperation with Sony Interactive Entertainment and then our Sony AI engineers to take advantage of a whole bank of PlayStations that were the rollout workers, creating an experience replay buffer that were then trained on a GPU. The sort of algorithmic nuggets here, we did use n-step returns, sort of a blend between TD and Monte Carlo, and introduced a new algorithm called quantile regression soft actor critic that did make a significant difference in performance. That basically was learning a distributional value function and learning two different critics using taking the minimal value of those to reduce overestimation bias, using a Huber loss on each of the different buckets in the distributional value function, and updating the policy also based on the minimum of the two Q functions. This was sort of the core of what we wrote about in the Nature paper, which you can find, and all the details are there. For those of you who are interested, the neural net was basically 4 layers of 2048 neurons wide. The input layer was sort of the state space. The output's just those 2 dimensions. It was designed to fit on a PlayStation, so everything is done once the policy is trained. Everything is computed on board, and we did things like standard things, like we have the twice as high learning rate for the critic than the policy, clipped gradients and dropout, things like that. But just to show you what it ended up with, so here's what training looks like after an hour, 4 hours, 8 hours, and actually in about a day it would get to this performance here. Training, so you see that it's not running off the track so much anymore, but it's not very good after an hour of training. 4 hours, it's significantly better, but it's really fine-tuned after a week. Sorry, and this, even after a day in this open track setting. This is sort of a histogram of the 100 best times by humans, and where GT Sophy was able to sort of fall on that. Sort of, the lap times got faster and faster after 4 hours, 8 hours. The previous built-in AI in the game was around here, and several seconds faster. And GT Sophy was its distribution over 100 different trials was right around the mean time of the best human driver. The second, third, and fourth, and fifth were significantly slower. And on the other car track combinations, it was significantly better than even the best human. I'm going to try to wrap up quickly, but there's a couple other, it's not just driving on an empty track. We also had to do the tactics and the etiquette. So to get into the multi-agent setting, we expanded the state representation to include the relative position, velocity, and acceleration of several different cars. We had to play around a lot to get the right representation of cars, but this is what it ended up working best. And then added a reward for decreasing the distance of a car in front of you or increasing the distance from a car behind you. Incentivizes passing and blocking. We then created specific training scenarios for the cars where they were either driving on an empty track or driving right behind one car or two cars or three or even seven. And then created a lot of experience in the kinds of settings that were sort of would happen rarely but were really important to learn. So it's sort of a curriculum in some sense. Things like a slipstream pass where you draft behind another car and then bounce out in front using your momentum to pass, or a crossover pass. I'll show some videos of those. So there's a bunch of different tactical scenarios, and then we curated the experience replay buffer, and this was another sort of algorithmic nugget was using a stratified sampling to make sure that there was the right amount of data of each of these types as a function of where the car was on its circle around the track. And that made a big difference in performance. So it ended up then being able to learn skills like this one, where GT Sophy starts behind the human driver. And you'll see it sort of bounces out from behind using the example of the slipstream to be able to pass. So that was an important skill to learn. Or the defense skill, being able to learn to block other agents. So here you see the GT Sophy in color preventing the 4 human drivers from finding a line. This was learned through experience by itself to sort of take this kind of a defensive stance. And then I think my favorite skill that it learned is this really sort of nice double crossover pass where you'll see that it looks like GT Sophy falls behind in position, and then by the time it comes out of the turn, both of the GT Sophy agents are in front of both of the humans because they've taken a line that sort of starts on the outside and crosses them on the inside. Then finally, there's this aspect of etiquette, and I don't have time to go into the details, but there's these sort of subtle rules that are very imprecise, where the car has to avoid not do avoidable collisions or force any drivers off the track or do things that are illegitimate. There's a human judge of context that when making these determinations, and so if it doesn't do this correctly, it can end up too timid, where it's in a winning position here, but ends up sort of getting too scared that it's going to get into a collision, and then ends up ceding to the human. So the announcer here thought there was no way that the person would be able to pass Sophy, but did, and we analyzed it later and found that GT Sophy put on the brakes. By the way, this setup is what we have set up here for tonight, so you can try racing in a seat like that. Of course, if it's too aggressive, it may end up pushing the car off the track. And this, of course, is not allowed. So it had to learn not to do that. So these were things that it did. In the first time we raced the humans, we had to then add some more reward components to sort of prevent that. And then there's an aspect that I won't get into here, but it's also covered in the paper. We trained, of course, many agents in parallel, but then we had to select just one to put in the real competition that counts. And there was sort of a very sophisticated method for doing that. Anyway, the punchline, we then played against humans in July of 2021 and lost. the first time. It was a race where there were 4 GT Sophys against 4 human drivers, where you get 10 points for finishing first, 8 for second, 6 for third, and then 5, 4, 3, 2, 1. We did well in one of the car track combinations, but not in the other 2. So of course we asked for a rematch. We analyzed the things that didn't go well. I'm going to skip through this because there's not much time, but then we did do the rematch in October and ended up very handily beating the humans by double their score, finishing first and second in all of the races. This is what landed on the cover of Nature, and we have some really nice examples of drivers saying that they've learned something from this. So here's Emily Jones.
It was really interesting seeing the lines where the AI would go. So there were certain corners that I was going out wide and then cutting back in, and the AI was going like in the whole way around. So I learned a lot about the lines, and also knowing what to prioritize. Like the AI into turn 1, for example, I was braking later than the AI, but the AI would get a much better exit than me and beat me to the next corner. So I didn't notice that until I saw the AI, and I was like, oh, okay, cool, I should do that.
So that's just a nice example. Finally, now it is deployed in the game. I think this is one of the most successful commercial applications now of an end-to-end reinforcement learning agent. And the details we can talk with you about at the demonstration. We've gotten a lot of fantastic feedback from the gaming community, but there's still a lot more to do. And there's some more challenges that I have listed here. One of the things that would be nice is to have the card drive with style. This is what you get if you increase in the reward function, sort of reward for drifting. The car decided to turn corners like this, and so we think that's a very stylish maneuver. But of course, we're now working with not just the studio Polyphony Digital that makes GT Gran Turismo, but many other game studios now are interested in incorporating reinforcement learning into the game. We're excited to do that. Again, this was the work of many people, as shown here. There's a lot of exciting things happening at Sony, but I'll just wrap up by saying, I'd love to be able to say that GT Sophy used all of the lessons that I talked to you about in the first part of the talk. That's not quite the case, but there's certainly choosing the algorithm to suit the problem. There's multi-agent interaction involved, building the agents. There is sort of some synthesis there as well. But I think these are all lessons that I think can be brought to bear. I've given you lots of different pointers of things that if you're interested, feel free to follow up with me by email, and I can point you to the papers. And with that, I thank you all for your attention.